All right, let's go ahead and get started. I do want to welcome you back to Unit 10. This is thermochemistry. I think a good place to kind of end this unit is by taking a look at the 2014 AP chemistry examination and looking at a question that had a part on it in 2014 that involved heats of combustion, right? Something that we know from this unit. So this is question number 6, part C, and here's how part C begins. It says, in a separate experiment, the student measures the enthalpies of combustion of propene and vinyl chloride. So the first thing to do is kind of relax and not panic. Enthalpies of formation. What do we mean by enthalpy of formation? Well, what we mean is the amount of heat per mole that is released when, in this case, propene and vinyl chloride are burned in the presence of oxygen. And we're going to go back into our memory banks and remember that enthalpy uses the symbol delta H. And I'm going to put a little C right here for combustion. So delta H of combustion is then what we're going to be looking at for propene and vinyl chloride. If you don't know the structure for propene and vinyl chloride, don't worry. These are organic molecules, and they're probably going to be given to us. If not the structure, then certainly the formulas for the propene and vinyl chloride molecules. So don't worry about that. The important thing is that you kind of get the gist of where this question is going. It has to do with thermochemistry. So you need to pull up everything that you know from the thermochemistry unit that we studied. It says the student determines that the combustion of 2.00 moles of vinyl chloride releases 2,300 kilojoules of energy according to the equation below. So they're telling me that this is the equation for the combustion of the vinyl chloride. And again, as I told you, they're telling me that this C2H3Cl is vinyl chloride. So it's 2 moles of vinyl chloride plus 5 moles of oxygen gas yields 4 moles of CO2 gas plus 2 moles of H2O gas plus 2 moles of HCl gas. All right. So in addition to the CO2 and the H2O, this time, because it's a vinyl chloride, has a chlorine here, we're going to get hydrochloric acid. So we're going to get carbon dioxide, H2O, and HCl in this process, but we're also going to get something else. We're going to get heat. In fact, we're going to get, according to the problem, 2,300 kilojoules of heat. Now, what if somebody wanted to know what the enthalpy of combustion for this was in kilojoules per mole? Now, they haven't asked me for that yet, but let's just say that I just needed to know that. Well, I would recognize that I'm going to get that much heat, but I'm starting with not 1, but 2 moles of the vinyl chloride. So I would have to say that the delta H of combustion is equal to 2,300 kilojoules divided by 2 moles, or 1,150 kilojoules per mole, just like that. Okay, so now I know the enthalpy of combustion per mole, 1,150 kilojoules per mole. But let me go further into the problem and see what they're actually wanting to know. It says using the table of standard enthalpies of formation. Now that's a little bit different than enthalpy of combustion, but that's okay. I know what that is too. Standard, by the way, means this. Standard means that I am measuring at 25 degrees Celsius and 1 atmosphere, for what it's worth. Below, determine whether the combustion of 2.0 moles of propene releases more, less, or the same amount of energy that 2.0 moles of vinyl chloride releases. Justify your answer with a calculation. The balanced equation of the combustion of 2.0 moles of propene is this. So now they're giving me another equation, this time with propene. They're saying that propene is going to undergo combustion. I'm going to get CO2 and H2O, but I'm also going to get some amount of heat in kilojoules. And my job is to determine, using a table of standard enthalpies of formation, what the amount of heat that is released so that I can compare it to the 2,300 kilojoules of heat released by the vinyl chloride combustion. All right, so let's go. Here's the table that they're giving me. So they're giving me standard enthalpies of formation in kilojoules per mole for C2H3Cl, that's the vinyl chloride, C3H6, that's the propene, CO2, H2O, HCl, and O2. Some of these numbers are positive, some are negative. The one for oxygen gas is 0, and that's exactly what I would expect for the formation of any element, even a diatomic element, okay? So here's one way that I could approach this problem. First of all, the heat of combustion in this reaction, the heat of combustion in this reaction right here is going to be equal to the delta H's of the products minus the delta H's of the reactants, okay? The standard heats of formation for the products minus the standard heats of formation for the reactants. So let's start with the products. So first of all, we'll begin with the CO2. Let me change pen colors here so it'll be a little bit easier to see. Let's do this color right here, okay? So we're going to start with the 6 moles of CO2, right? Right there. So 6 moles of CO2, and CO2 has a heat of formation of minus 394 kilojoules per mole. So I'm going to say 6 moles of CO2 times minus 394, don't forget the sign, minus 394 kilojoules per mole will give me the amount of heat that's released in the formation of the CO2, the 6 moles of CO2. So that takes care of the 6 moles of CO2. How about the 6 moles of water? Well, what I'm going to do here is I'm going to multiply 6 moles of water times water has a heat of formation of minus 242 kilojoules per mole. So I'll say 6 times minus 242 kilojoules per mole. Again, moles and moles will cancel. I'm left with kilojoules. So now I've determined the delta H for the products. So now let's go to reactants. Minus the C3H6. So 2 moles of C3H6, that's the propene, times 21, and that's a positive, so be aware of that, positive 21 kilojoules per mole, and I'll multiply those two together. But where's the oxygen? Well, I didn't even include it because, look, oxygen, its heat of formation is 0. Again, they didn't even have to put that in the table for me. I know that heats of formation of any element, including diatomic elements, is going to be 0, so I don't even bother to include it in my calculation. So now let's add things up. We've got 6 times minus 394. When I do that on my calculator, I get, and check me on this, minus 2,364 kilojoules. Plus, now let's do 6 times minus 242. I get minus 1,452 kilojoules. Now let's subtract that 2 times 21, 42 kilojoules from the propene. And when I say put all this together, what I get as my final calculation is minus 3,858 kilojoules of heat. Okay? So, in other words, according to this calculation, according to my calculation, this number right here is now known. I've used heat of formation data to calculate that minus 3,858 kilojoules is liberated. So I'm going to add there minus 3,858 kilojoules, I now know, is going to be more in terms of energy when I compare it to the 2 moles that were of the vinyl chloride that was undergoing combustion, right? You know what? This should be a plus, so that's not a negative number. It's exothermic, so I'm getting that amount of energy. So obviously the amount of energy upon combustion of the propene is going to be more than the amount of combustion heat, the heat of combustion for 2 moles of vinyl chloride. And I would state that in my answer. But before I do that, I want to actually work this problem a different way. Okay, that would have been a perfectly legitimate way and certainly absolutely correct to do that. And at that point, I would simply state what I've just told you, and that is that the heat of that is released upon the combustion of propene is more than that of the vinyl chloride, right? That was the question. Let's try this a different way. Here's that reaction again. It's 2 moles of C3H6 plus 9 moles of O2 yields 6 moles of CO2 and 6 moles of H2O. I want to do it a different way this time, though. What I want to do is I want to take the reactions, the actual reactions of formation, right? And I want to, from the table, write down the heats of formation. So I'm going to take the heats of formation for everything, right? So I want to start with the C3H6 that we see, the propene that I see on the left-hand side. So what is the reaction that produces it from its elements? Well, carbon and hydrogen are the only two elements. Carbon would be monatomic, hydrogen diatomic, so it would be 331. Remember, these numbers all have to be ones in the formation reactions. So from the table, I determined that the energy of formation for C3H6 per mole is 21 kilojoules per mole. I do the same thing with O2. Again, it's going to be 0. All right. I do the same thing with CO2. This time minus 394 kilojoules per mole. And I do the same thing with H2O. This time I get minus 242 kilojoules per mole. Now watch what I'm going to do. I'm going to use Hasse's law to rearrange these equations. The first one I'm going to do two things to. I need C3H6, but I need it on the left-hand side, and I need 2 moles of it. So I'm going to flip it and double it. When I take 2 times 21 and then give it the negative sign, I get negative 42 kilojoules for that first process. The next thing I'm going to do is the O2, I need it on the left-hand side, and I need it multiplied by 9. So I have 9 O2 on this side. This is 9 oxygen and 9 oxygen, I suppose. But the point is that when you multiply 9 times 0, you just get 0. So it really doesn't affect me there. The next thing I'm going to do is I'm going to take the CO2. I need CO2 on the right-hand side, but I need it multiplied by 6. So I'll multiply it by 6. But Hesse's law says if you multiply the reaction by 6, you have to multiply the delta H by 6. That's what I've done. I get minus 2,364 kilojoules. And then finally what I'm going to do is I'm going to take, I need 6 H2Os on the right. So I'll multiply everything by that number, and what I get is 6 times minus 242 kilojoules per mole. That's going to give me minus 1,452 kilojoules. Now what I'm going to do is I'm going to add all these up, all right? So remember, when I do all the canceling over here, I'm going to get what I had originally in the original equation, this equation right here. Let's look at it one more time. It was 2C3H6. Let's see how we would get that 2C3H6. Well, sure enough, there it is, right? Now, we don't have any carbons, so we're going to get rid of this carbon, and we're going to get rid these 6 carbons, rather, and we're going to get rid of these 6 carbons, right? We also don't have any hydrogens, so I'm going to get rid of these hydrogens, and I'm going to get rid of these hydrogens, just like that. Let's go back up to the equation and see what else we do need. On the left-hand side, we're going to need 9 O2s. Where do we get them? Well, notice that I'm going to take these oxygens and these oxygens, and I'm going to get rid of these and get rid of this and this, leaving me with 9 oxygens on the left-hand side. And now let's go to the right-hand side. What I'm going to do is when I go to the right-hand side, I need 6 CO2s. Let's see if I can get those 6 CO2s. Yep, they're right there, right? They're right there. So now I've got 2 C2H3s on the left. I've got 9 O2s on the left. I've got 6 CO2s on the right. And now all I need is 6 H2Os on the right. There they are. So again, if I add everything up and cancel out what's common on the left and the right, I should be able to get the same number. So there it is. When I add them up, I get minus 3,858 kilojoules of heat. And here's how I'll report my answer. The heat of combustion of 2 moles of C3H6, that's propene, is greater than that of vinyl chloride. The calculated value for the combustion of 2 moles of propene is minus 3,858 kilojoules. The reported value for the combustion of vinyl chloride is only minus 2,300 kilojoules.